In this video I will show you how you can apply Ohm's law in practice, the famous law that connects voltage and current in a very simple manner, and the goal here is to gain experience with Ohm's law by measuring different quantities in a circuit and then by applying the correct formulas to find out unknowns which you are looking for. My name is Andreas from The Fearless Engineer, and here we go. Now, before we dive into the application of Ohm's law in the upcoming video, let's briefly discuss the motivation why it's important for you to know about this concept and also to watch this video. If you have seen any of my previous videos, you will have heard about Ohm's law, and you will also know that it's one of the basic equations which we have in electrical engineering and electronics. It connects two values, its current and voltage, via the electrical resistance of the material through which the current moves. And this makes it possible to calculate unknown quantities from known quantities in a circuit. Let's assume you want to know which voltage drop you have across a resistor in one of your circuits, and if you know the resistance value of this resistor and if you know the current flow through the resistor, then you can compute the voltage drop across the resistor using Ohm's law. And there are several other applications which make this law very useful. And in this experiment, this video here, we're going to do two things. First, we want to compute the current flow from voltage drop and from resistance, and secondly, we want to compute voltage from current flow and also resistance. These are the basic experiments which we want to conduct here. Before we do so, again, a quick bit of theory here. We have already talked about this relationship that Ohm's law establishes between the two values, and important to know is also that it's only defining a linear relationship between these two, between current and voltage, which means the resistance value R, which you can see here in this small triangle, the resistance value R is constant for all currents which flow through the resistor for which this value here holds. And this is not the case for all materials. For a proper resistor which is used in electronics, we can assume that it's going to be an ohmic behavior, which means R is constant over all values for current, at least in moderate dimensions. There's going to be some point when the ohmic behavior of a proper resistor breaks down, when we make the current too large, but for most values up to a certain level, we can assume it's going to have an ohmic behavior. But there are other materials for which this property does not hold. For example, a light-emitting diode or a PTC resistor, for example. And using Ohm's law, that's the second item here on this slide, we can calculate a third component if we know the first two. So we can calculate the voltage, we can calculate the current, and also we can calculate the resistance if we know current, voltage drop and current. And by using this neat triangle here, you can easily remember the shape of these equations by looking at the geometrical relations between the two. Now let's look at the experimental procedure which we're about to see. First, we will measure the resistance value without connecting it to a circuit. This is what you can see here in this small diagram. We will directly connect this multimeter to the terminals of the resistor, and because the multimeter is using a small current flow through the resistor and then measuring the voltage drop to generate its value for the resistance of this device, we cannot connect anything else to it. Otherwise, this small current generated by the multimeter will flow elsewhere, and we will have a falsified reading, because not all the current which we send into this connector here will come out at the other end and will be available again to compute the resistance value here. So this has to be disconnected from any circuit which it might be connected to. Secondly, we're going to measure the voltage drop across the resistor, which can be done in the fully connected circuit. And in this circuit here, we're going to connect a battery to the resistor here in a closed loop, no other branches here, only a resistor directly connected to a battery. If we then connect the multimeter to both the input and the output side of the resistor, we can directly measure the voltage drop. And by using these two values, resistance value and then voltage drop given a power source, we can calculate the current from both these measurements using Ohm's law. And next we want to measure the current through the resistor. We're going to take the same current but disconnect the output of the resistor to the cable leading back to the terminal, the positive terminal of the battery, and instead we insert the multimeter in between the circuit, which still makes it an unbranched circuit, but now it's leading through the multimeter here, which we set to amperage measurement. And in doing so, we can take the reading of the current running through the resistor. And by using our resistance measurement from the previous slide and our current measurement, we can again use Ohm's law to calculate the voltage both from current and resistance. Now, the aim of this experiment is to observe Ohm's law in action. Ohm's law states that we have a linear relationship between voltage and current, which is determined by the resistor through which electricity is conducted. This has to do with the loss of potential energy, and we have talked at length in several videos about this topic already. Now, what you can see here is a series of 10 kilo ohm connectors, which is pretty high in comparison to the resistance of, let's say, a cable, for example. A typical copper cable of a length of 1 meter usually has far below 1 ohm of resistance. So 10 kilo ohms really is a lot of resistance against which the electrons need to struggle in order to move through the material driven by the electric field. And before we observe Ohm's law in action, let's actually measure the resistance of one of these resistors, because there's going to be some differences between these. Even though they look all similar, we have one of these colored rings which gives us the tolerance of the resistor, and the tolerance says that not all the resistance values are going to be similar, but they're going to be deviations. And we want to know exactly what resistance value is behind the resistor we're going to use for our experiments. So in order to do so, let's switch the multimeter on the left side to ohms. What you can see here is all the range of measurements which we can take with this multimeter here: voltage and current and also capacity, and now we're going to measure the resistance value by using the ohm symbol here. Now, in order to do this, we only need to connect these two measuring tips against one of the resistors and observe what's going to be displayed on the display here. Now, the resistance value you can see here is not 10 kilo ohms, it's 9.87 kilo ohms, which is less than what we were promised, so to speak. And to check what the other resistors have in terms of their resistance value, let's connect these crocodile clips to the second resistor, which is at 9.93 kilo ohms. So a slight difference, still within the tolerance, but nonetheless, if we want to observe Ohm's law in action, we need to know exactly what the resistance value is going to be. So for our experiment, we're going to use this outermost resistor, which has a value, as measured before, of 9.87 kilo ohms. Now, in order to test the validity of Ohm's law, what we need to do is we need to hook up a power source to this resistor here, and the power source is an adjustable power source, which currently is set to a voltage of 5 volts, which is what will drop across this resistor here once we connect these clips leading to the power source and switch it on. As of now, it's still switched off. And what we will also do is we will set this amp meter here to voltage measurement, connect the red lead to the positive terminal of the voltage source and the black lead to its negative terminal. Okay, so now we have the two connected, and let's switch on the power source. And as you can see in the display, the entire voltage drops across the resistor here. The voltage source has been set to 5 volts, and the voltage drop across the resistor is 4.995996 volts. And the rest drops across the lines, the copper cables leading to and away from the resistor here. And in order to observe Ohm's law, let's now measure the current flow through the resistor. And before we do so, let's switch off the power source. And now reconnect these measuring tips. And in order to measure the current flow, we need to integrate it into the circuit, the multimeter. And before we do it, we set it to measuring amps. And what we also need to do is we need to connect the amp meter directly to the resistor. This is the connection leading to the amp meter. Now the current flows through the amp meter, leaves the amp meter through the red cable here, And if we connect the red cable, leaving the amp meter, directly to the negative terminal of the power source, the current now enters the resistor from the right, leaves it on the left, flows through the black cable, enters the amp meter through this terminal here, displays the current flowing through it, and leaves the current meter through the red cable, which ends up here, and the black cable you can see connected to the red one leads back to the power source. So we again have a closed circuit. Now before we start the actual measurement, let's take a quick look at this cable here. We have used it for measuring the resistance of the resistor and also for voltage measurement, but as you can see there is no amperage symbol. This is only on the left side here. The reason behind this is that this multimeter prevents against a large current flow by having an appropriate fuse inside. So we have a maximum of 10 amps which we can safely let flow through this multimeter before the fuse blows. But in this setting here, even though we have adjusted the rotating selector wheel here, we cannot measure current flow. In order to do this, we need to plug the cable to the left side. And now we are good to go. Let's activate the power source. And as you can see here, we are observing no current flow at all. We have a small disturbance here in the third digit, but apart from that, there's absolutely no indication that any current is flowing here. And the problem is that we are really using a very high resistance value here. We have a 10 kilo ohm resistor and we only have a 5 volt power source. So basically what we can do is we can do two things. We can increase the voltage. Let's do this for just for the sake of completing this first phase of the experiment. Let's set the voltage source to, let's say, 20 volts. Now we are at 20 volts, and what you could see is that the last digit now has changed to 0.02. So there seems to be something going on. Now the problem here is that this amp meter, which we are using now, is not appropriate for measuring very small currents. And the current which is flowing due to this high resistance value of 10 kilo ohms really is very, very small. So in order to still finish this experiment successfully, what we have to do is we have to use another multimeter just for this purpose. Let's unplug this one here and switch it out for an almost identical one, which is able to measure very small currents. What you can see here is that it's going to measure microamps. So 1 microamps is 1/1000th of a milliamp, and this is what we're going to observe here. But before we switch it on, let's go back to our setting of 5 volts just to be able to compare it to the voltage measurement which we took before. And now let's turn it to measuring microamps. And once we switch it on, you can see that there's actually a current flowing here. It's 383 microamps, which is 0.383 milliamps. And this is the reason why we couldn't see this current using the other multimeter. So in order to measure very small currents, you really need to make sure that you have an appropriate measuring device. That's also one learning element you might want to take away from this experiment, apart from being able to calculate the resistance from a voltage and current measurement. Always use the right measuring equipment. So what we have observed now is a voltage very close to 5 volts and a current below 1 milliamp, in this case 383 microamps. And now let's find out, by applying our equations, if those measurements really are leading to the same resistance value which we saw here printed on the label of these resistors. Now let's look at the results of our small experiment here. First, we have computed the current I from our measurements of voltage and resistance. We have used a 10 kilo ohm resistor, measured it, and arrived at a reading of 9.82 kilo ohms, which is close but not exactly at 10 kilo ohms. We have also measured the voltage drop after connecting a power source to the resistor, which was at 4.995 volts. And this leaves us at a current of 0.51 milliamps running through the resistor from the power source. And secondly, in this experiment here, we will now be using a current measurement and the same resistance reading as taken in the last video to arrive at the voltage drop across the resistor, which by using Ohm's law is now at 3.77 volts. Now the question might arise why the voltage drop which we calculated is smaller than the measurement which we took in the first experiment. If you have any idea why this might have happened, please drop me a comment down into the comment section below and we will continue our discussion there. That's all for now. If you have any questions related to this video, don't hesitate to drop me a comment down below in the comment section. Also, if you have any suggestions for future videos which you want me to make, please also leave a comment here. I wish you a nice day now, all the best, and see you next time here on The Fearless Engineer.